To show the changes in the riskscape, I have considered two different model outputs, CMIP5 and CMIP6. And based on the differences, I would show the implications of the changes in terms of food security. So when we talk about food security, in this study, we have considered only drought as a hazard. So let's look at the drought scenario in Southeast Asia. SCAP estimated that in past drought in 2019 and 2020 El Nino, around 70% of the land area were affected by drought. 15 to 20% of population were living in drought hotspots, and mostly the most impact of drought was absorbed by the agricultural sector, and also it affected the GDP. So while the number of fatalities is not that high in terms with respect to the other hazards, but if we look at the number of people affected due to drought, it comes in number 3 after flood and storm. So and the number of population affected is relatively high. So drought in recent past mostly affected the northern and central part of Thailand, northern part of Laos, northern part of Vietnam, northern part of Myanmar during 2015 and 2020 due to El Nino. But when we look at the future scenario, in this study we have considered consecutive dry days as a proxy of drought, and we have considered two different warming scenario, 1.5 degree, and 2 degree scenarios, and two emission scenarios, 4.5 and 8.5. So from CMIP5 to CMIP6, we can see that there has been a change in the reduction of the area under potential drought under very high to very high category. Similarly, if we go to the 8.5 scenario, we have found that there has been a 45% decrease in the area under high to very high probability of drought when we considered consecutive dry days. And most of that, in both the cases, the area under potential drought is mostly concentrated in the southern part of Myanmar, central part of Myanmar, and eastern part of Thailand, and also in Timor-Leste and southeastern part of Indonesia. Along with consecutive dry days, we also considered mean temperature changes in between two modeling output, because although drought is in Southeast Asia is manifested due to extended period of below average precipitation, but above average temperature can also exacerbate the existing drought condition. The analysis showed that the projected increase in the mean temperature in the possibly drought-affected areas in the future scenarios, in both the scenarios. However, from CMIP6 to CMIP5 to 6, the areas with high to very high categories has changes its spatial distribution. And when we calculated the areas under potentially high and very high mean temperature, we have found that there has been a little bit decrease, around 0.64% of decrease in the area under RCP 4.5, and in case of RCP 8.5, it is around 1.4% decrease in the areas. So rice is the main agricultural product in Southeast Asia, both in terms of domestic consumption as well as export. So when we see the exposure of rice producing areas and rice production as a quantity, from CMIP5 to CMIP6, we have seen a drastic reduction in the exposure of rice produce, the amount of production. In CMIP 6, the exposure is much, the rice production quantity exposure is much less than CMIP 5 when we use the consecutive dry days. And also in terms of when we consider mean temperature, we found a contradictory result. So we thought to take both the variable together and see if to consider on the areas where both consecutive dry days and mean temperature has equal impact on the rice producing areas. So what we saw that though the areas under high exposure is reduced from CMIP 5 to CMIP 6, but some of the areas are very highly rice producing areas. For example, the southern part of the delta part of Myanmar and the central eastern region of Thailand, which are exposed to both extended period of dry days and mean temperature. Similarly, in case of RCP 4.5, we found the similar kind of scenario where though the area under production has reduced, but the highly rice producing areas has been exposed in Myanmar and Thailand. So when we compare the scenarios with taking both dry days and mean temperature together, we could see that especially in Myanmar, in CMIP 5, which is showing an increase in the rice producing exposure of rice producing areas in CMIP 6, considering both the variables, than from CMIP 5. Now, Myanmar is the areas which are exposed is very highly rice producing area. It is a Irrawaddy river delta area, and they are prone to drought risk. And this area and also the central part of Myanmar, where the drought risk is like high drought risk has been found. Those areas are socioeconomically poor, and high malnutrition scenario is there. Like 6% of children are severely stunted, and 24% are moderately, and economically also 27% of working men are they are working in the agricultural sector. So policy-related decisions should focus on the east, to the eastern part of Thailand and the central and southern part of Myanmar. So as we try to conclude that this is the entire scenario, how it is changing the riskscape from CMIP 5 to CMIP 6. And they have implications in the food security. Among the 4 different pillars of food security, it is going to affect the 3 pillars, which are availability, supply of food, access, equitable distribution, and stability, permanent and durable access to food. So thank you very much, and these are my other contributing authors who worked with me to develop this work. Thank you very much for your attention, and any question.
We now have a minute or two for questions. So does anyone have anything they'd like to ask? I'm curious more about how the increase in dry days may affect food security in areas with higher vulnerability.
Any specific region you mean? So increase of dry days, actually the parameter says the dry days are described as when rainfall is less than 1 millimeter. So if there is increasing number of dry days, especially in the wet season, if it happens, then it triggers drought. So I think that's how it can affect the production as well, and the food security in terms of production. Yeah.
Do we have any questions online? Nope. Okay. Well, thank you so much.
Thank you very much.
To our next speaker.
Okay, so now we'll hear from our invited speaker, Faji Mena, on the impacts of anthropogenic activities and changing climate on land surface processes in high mountain Asia.
You can hold the mouse.
Can you hear me? I can stand from here.
Yeah, I think the mouse might, you can hold the mouse with you over there.
Okay.
Yeah, absolutely.
Okay, so hi everyone. So on behalf of my co-author that are listed here, I'm going to present our work on high mountain Asia, more precisely how the changes in land surface processes over the past decade in high mountain Asia. Okay, so high mountain Asia is home to Asia's most prominent river basins, such as the Yangtze, Indus, Ganges, and Irrawaddy Basin, and is home to over 1 billion people. At the same time, HMA, or high mountain Asia, is one of the most vulnerable water droughts on Earth. The warming that's happening in high mountain Asia is actually double the global average. And high mountain Asia is experiencing a huge decline in groundwater that is primarily due to agricultural activities. As you can see here, that over the Ganges and the Indus Basin, we do have a huge decline in groundwater resources. High mountain Asia, again, is experiencing one of the highest rates of greening on Earth. You can see on the right, we do have greening on Earth, and then if we zoom in on the left in high mountain Asia over the Indus and the Ganges-Brahmaputra Basin. So our objective here is to understand the link between changes in climate and anthropogenic activities and how these changes impact our land surface processes, such as like greening in high mountain Asia. To do so, we need to understand the hydrology or the land surface processes in high mountain Asia. The problem is observational scarce. Observational critical to understand the hydrology of a region. These observations are scarce because of the harsh environment of high mountain Asia. So remote sensing or the analysis data are critical to understanding the dynamics of high mountain Asia. In this study, we rely on bodies leaf area index LI, albedo, snow cover, GRACE, TWS, and other remote sensing data. So our main objective here is to identify the drivers of greening in high mountain Asia. To do so, we use a partial information decomposition. This is coming from a paper that was published early this year, and you can scan the QR code to have the paper. So if you think about the vegetation growth in high mountain Asia, there are two sources of vegetation growth. One can be snow cover because we have warming, so either like the growing things is getting longer, or soil moisture. We have greening in high mountain Asia simply because we have an increase in soil moisture. So to identify the causes of greening in high mountain Asia, we use a partial information decomposition. In this approach, when we took the leaf area index, we can try to identify the contribution of soil moisture to the leaf area index, the contribution of snow cover to the leaf area index, or how the soil moisture and snow cover interact to drive the changes in leaf area index. So trying to identify these processes, if the unique contribution of soil moisture to the leaf area index is the highest and the area is irrigated, we deduct that greening is due to irrigation. And if not, we do have an increase in precipitation, meaning that we have greening in the region because we have an increase in precipitation. On the other hand, when we have the unique information of snow cover that is the highest, we deduce that we have a warming-induced greening. And sometimes we can have both soil moisture and snow cover that are governing the changes in leaf area index. In that case, it's also due to warming because snow cover decreases are going to induce an increase in soil moisture. So looking at the result over the high mountain Asia in terms of contribution of soil moisture that we have on the left, in the Indus and the Ganges basin, we have a huge contribution of soil moisture to the changes in leaf area index. And this soil moisture basically coming from irrigation is driving greening in the region. If you zoom over the Irrawaddy basin, we have soil moisture that is contributed to greening, but we do not have irrigation. Rather, we have an increase in precipitation. Over the Tibetan Plateau and the Himalayas, it's both soil moisture and snow cover that are governing changes in leaf area index. And this greening is due to warming. But if we zoom in over the Yangtze Basin, it's only the snow cover. And this is because the snow cover is decreasing, so we have longer growing season. So we came up with a map of the drivers of greening over high mountain Asia. Warming, so changes in climate in red, actually is driving most of the greening in the region. But at the same time, you have irrigation and precipitation. Irrigation in blue, precipitation in green. And if we zoom in, looking at how the leaf area has changed over the past year, actually irrigation is driving the highest rate of greening in the region. So these changes in greening and leaf area index can impact surface albedo because we are at the land surface, and this can impact the energy balance in the region. Looking at how surface albedo has changed over the past 2 decades in high mountain Asia, we have a directional trend. In blue, an increase, and in red, a decrease, but we have mostly a decrease. So what can potentially cause changes in surface albedo in high mountain Asia? We have warming, snow cover is changing, the albedo is changing. We have greening because vegetation is changing, and also irrigation because the soil moisture is increasing. So in a paper that came out in September, we analyzed the causes of surface albedo, changes in surface albedo in high mountain Asia. So as I said, like snow, LRI, and soil moisture can all impact surface albedo in the region. So we use the same parcel information decomposition that I presented before to understand the drivers of the surface albedo in high mountain Asia. We came up with a map of the drivers of the changes in surface albedo in the region. In blue, we have areas where snow cover is driving the changes in surface albedo. In brown, we have areas where soil moisture is driving the changes in surface albedo. And in green, like most of the areas, we have vegetation, so leaf area index that is driving the changes in surface albedo. If we look at the Amu-Darya basin, throughout the year, depending on the season, like soil moisture in brown can have a huge impact on the surface albedo, but mostly if it is LI. Over the Yangtze and the Huangpu basin, basically, LI is the dominant driver. But if we zoom in, like in February, we have a huge contribution of snow cover because it's during the winter. Over the irrigated basin of the Ganges of the Indus, for sure, is soil moisture like all throughout the year. And in central Himalayas, we have both, like, although the snow cover is a dominant driver, we have like significant contribution of soil moisture and leaf area index. So coming back to the changes in leaf area in surface albedo over high mountain Asia, like we can see again that in the Indus and the Ganges, those are the areas where we have a huge decline in surface albedo, and this corresponds to the irrigated lands of high mountain Asia. So to wrap up, high mountain Asia is going through a lot of changes in land surface processes, decreases in snow cover that's coming from warming, greening, increases in soil moisture from irrigation. All these factors impact the changes in leaf area index and cause greening in the region. But the highest rate of greening in high mountain Asia is caused by irrigation. Mostly surface albedo is decreasing in high mountain Asia. And irrigation is again, irrigation due to anthropogenic activities is again like one of the highest the dominant driver of the changes in surface albedo in the region. So if you think about changes in climate and anthropogenic activity, irrigation coming from this anthropogenic activity could change the water and energy cycle in high mountain Asia. And if we think about like mitigating the impact of climate change, we need to be able to account for these human practices such as irrigation. Thank you.
We have a few minutes for questions. Does anyone have any questions for Faji? I think there's a.
This shows that irrigation is the main cause of the breeding, and at the end you also said that many of these anthropogenic activities has to be reduced to manage the climate change. But as you know that in this part of Asia, irrigation is the main source for food. That's the agricultural crop. So if we are reducing these type of activities, how do we ensure food security of this country?
I think it's not matter because like irrigation has been like, it's like not irrigation, it's because it's happening like it's intense irrigation that is happening in the region. So everything, if it's in excess, it's become like not feasible to sustain, right? So it's not like stopping irrigation, but thinking about a sustainable irrigation that's not going to damage the environment, because right now the irrigation that is happening there is like damaging the environment. Why not like trying to spread the agricultural area, or trying to think about ways of we are going to compensate for the impact of irrigation on our water cycle by other things. Yeah.
Any other questions? I have one question. Really great presentation. I was curious, can you go a little bit more into detail on like what kind of downwind effects decreased snow cover or albedo could have on water resources in the region? You kind of touched on it a little bit in your last slide.
Okay. So when we have like a decreasing snow cover, so the albedo decrease, it's like trigger the warming like process. So it's we have like more the water is going to be, the soil is going to be warmer. So like more ET probably, and other factor that is going to impact the water cycle. On the other hand, also, so it's like really to understand the water resources issue is going to be like complex, because we have to understand that snow is going to decrease albedo, but sometimes like if you have like over vegetated area, if you have a decrease in albedo, we can have more precipitation, right? And currently, exactly that, to be honest, that's not something that we are like, it's the direct impact of the increase in precipitation is observed in some area, but not really. But I think like the decrease in albedo can actually lead to like a warmer soil and more drought probably.
Thank you.
Thank you so much. Our next speaker is Franz Meyer, presenting on HydroSAR, developing and transitioning a SAR-based inundation monitoring service for the Hindu Kush Himalaya.
Do we need to do anything? Okay.
You send a piece.
Yeah, PC. Right. Only PC. Only PC session. Okay. Excellent. Yeah, so welcome all. I think we are switching into hydrology mapping for a couple of talks. So if you're interested in that, stick around also for Yonki Lee, who's giving the next presentation. So I want to talk about HydroSAR, which is a monitoring service, an inundation monitoring service that was developed for the Hindu Kush Himalaya in the framework of a NASA Severe grant. The grant was led by myself. My name is Franz Meyer from the University of Alaska Fairbanks. But we worked very closely with partners at the Marshall and Goddard Space Flight Center for this, as well as with our partners in the region at ICIMOD, specifically Rajesh Thapa and his colleagues. So the reason why we collaborated with ICIMOD on this work is that it was acknowledged that many nations in the Hindu Kush Himalaya are increasingly suffering from severe inundation and flooding events. Yet the disaster risk reduction systems in the region, they often lack near real-time or low latency access to information on flood extent, flood depth, and impact on agriculture and similar parameters. And so we were convinced when we proposed this in 2018 that modern data sets from modern SAR systems that have now routine observation characteristics and have, of course, cloud penetration can really make an impact on providing data sets over large areas, independent of weather conditions, and at a low latency time frame. So what HydroSAR in the end did, to summarize that up on one slide, is we developed or worked on two areas. One of them is the development of SAR value-added products, so automatically derived data sets that are useful in monitoring hydrology. The two on the left-hand side, those are more visual aids. So those are fully calibrated image time series. We also have a colorized SAR product that sort of emulates the look and feel of an optical data set, shows water as blue, for instance, in most cases. And that's also useful for just visual analysis of remote sensing data sets in a cloud-free environment. The other four are more quantitative products. The ones I want to talk about most today is the Hydro 30 flood water extent product, as well as a flood depth product, the FD 30 product. Both of them are 30-meter products derived from Sentinel-1 SAR data. Because SAR is a very large volume, high repeat cycle kind of data set, data volumes become very large very quickly. So we also focused on developing cloud-based resources that are integrated with NASA's data centers that are nowadays moving into the cloud. We're using two services that were co-developed with the Alaska Satellite Facility. One of them is a production pipeline that is called HYPE. We use that to create data quickly over large spatial scales. And we use a platform called OpenSARLab, which is more an algorithm development platform that sits in the cloud next to the data set. We used it for our own development, but we also handed it over to the partners at ISTIMAT to be able to expand the product portfolio with new algorithms. Just briefly, the water extent approach is, because this is an applied science project, we set up on really on the shoulders of giants here. So there's a paper in 2016 or 2015 that was published by Sandro Martinez and his colleagues at the German Aerospace Center. They developed a good first approach for doing thresholds-based water extent mapping in a robust manner from SAR data. The approach utilizes the fact that open water looks dark in SAR images, and a threshold approach is quite successful in mapping those the extent. We are following a workflow that's very similar to their publication. We start with fully geocoded calibrated images. We call those RTC, radiometric terrain correcting data sets, corrected data sets. And then the meat of the approach is in the second step, where we do automatic thresholding by basically we tile the image into smaller tiles. We then have an algorithm that finds tiles that are about equally touching water and land. Those have often very nicely bimodal distribution. And then we have an automatic, we use an automatic thresholding approach that then finds the best separation point between those two modes. And so we get that, we do that for 5 to 10 tiles and then average the result, and we get an adaptive threshold for every scene. Once we have that, we get an initial map of water candidates. We do some post-processing to throw out false detections and fill in some holes. This is done using a fuzzy logic framework that uses a number of different criteria. We then pull in permanent water from other resources and then push the data product out to a web platform in a cloud-enabled GeoTIFF format. The approach works quite well. This is here comparison. This is here over the Missouri River in this case, which is good for validation because there's flooding in the spring, but there's also a lot of clear days. So we can use optical data to sort of cross-reference with the SAR data sets. And this animation may show you that while the two data sets at a pixel by pixel basis have off and on differences, if you sort of look at the progression of the flood, both optical and SAR data sets capture the progression very equivalently. We set up on the water extent that we derive in the Hydro 30 product, and we have a follow-up approach to calculate flood depth. And this is sort of a notional meter scale flood depth estimate. The goal here is more to understand are crops completely submerged in vegetation? How many floors of a building are submerged to understand these kinds of parameters? And so what we do is we use the water extent map that we derived in the previous step, and we marry it basically with DM information. We use the Copernicus Glow 30 DM. We derived from it a height above nearest drainage data set using hydrobasin information. If you're interested in that data set, let us know. This is a first time, I think, a hand data set was derived from that DEM. We have a global product. If you're interested in that, let us know. And then we have an approach, sort of an iterative approach that tries to estimate the most likely true flood depth by minimizing a forecasted flood depth based on the DEM data we have available to the forecasted water extent to the measured water extent. Minimize those two. To be efficient, we use a basin hopping approach, which is sort of an efficient way of finding the global minimum in a solution space. This seems to work, at least for the Hindu-Kush Malaya, quite robustly. This is a data set here near Dhaka from, in this case, 2019. We have a number of data sets that we're looking at here. We are comparing, in this case, the water depth that we calculate from SAR data. This is on the x-axis. Two measurements, in this case, from river gauge stations that we got from the Bangladesh Water Board. This is shown on the y-axis. And you see that the correlation between those two is pretty good. The standard deviation or the RMSE between them is in the order of about 1 to 1.5 meters. And that's part of what's expected because in the end, our water depth estimate is only as good as the underlying DM information allows. So one thing that was kind of new and it's kind of partly enforced by the pandemic is we ended up all working on this from our living rooms, basically. And so we actually made extensive use of our own cloud platforms to run this entire project. So in the end, this entire project was end-to-end developed fully in the cloud. So we leveraged ASF's cloud-based data resources. We did the code development and algorithm development and all the calibration validation using OpenSARLab, which is this cloud-based Jupyter Notebook platform. Once we had the codes finalized, we Dockerized them and we dropped them into our operational pipeline, which is the ASF High pipeline, where they then get created scalably directly in the cloud. The products are stored in an Amazon S3 as cloud-optimized geotiffs and are served out from there using cloud-enabled Esri image services through the help of Esri developed with them. And then on top of it, end users are building web interfaces. So this is the web interface that was developed by Isimot. You can, I think I have a URL on the last page. And so if you go there, you can scroll through the time series and analyze the progression of flood over time. I want to say at the very end, the last year of the project, we are wrapping up the project now, was really focused on transition. So we wanted to be able to walk away from the project knowing that Isimot has the capability to run the service on their own in different ways. We facilitated that in two ways. We tried to develop tools that are modular so that Isimot can decide to either run the entire service locally or to cut it up at different pieces and run portions of it locally. And then we wrote up a transition plan that documents different ways how the service could run and had a separate workshop at Isimot to work with their team so that they have full understanding how to operate the service long term. For end user trainings over the years, we started out initially having more hackathon type trainings with end users where we wanted to make, give them trust in the product. So there we really talked about trying to help them understand how the products are created, what assumptions are in the product, and what the accuracy metrics are. And then later on, we focused more on end user trainings on the usage of the products, as well as the usage of the platforms that were the web platforms that were developed in collaboration with Isimot. So in the end, it's a service that's now running operationally. It has been monitoring the monsoon season in the Hindu-Kush Malaya for now 2 full years. We've transitioned all services into the operational platform and have handed over the keys to Isimot. So if you are interested in looking by or stopping by the web platform, there's a QR code that you can look at. If you're interested in following what we are doing with HydroSAR and other projects, there's also a little QR code to our Twitter feed where we host and post updates over time. And lastly, I want to say, if you're not yet connected to Severe, you should talk to this team. It's a really fantastic organization that's fun to work with. And so if you want to know more, talk to the hosts of this session. Thanks a lot.
Thank you so much, Franz. Are there any questions? There are no questions. I have one for you.
I was about to walk away.
There are a lot of challenges to working with SAR. So are there certain scenarios, either temporal or kind of physical scenarios in topography where your product works better than others?
Oh, where the product works better. Yeah, so I think the big benefit of the service we developed is that it runs automatically. So you get a product and a result within an hour after the data sets become available. So the latency from acquisition to getting a product is short. There are still limitations. We are creating our products at 30 meters. There are some valleys, certainly in Bhutan and in Nepal, where we have issues with detecting the open water because we have poor visibility into those canyons with the side-looking geometry. Another limitation that maybe is a good transition to the next talk is that we, with our service, are still reliant on the observation cadence of the radar. So we get a product whenever the satellite acquires. And so Hyunki, I think, is going to talk about, about fear and how you can use other information to densify or interpolate or forecast, whatever you want to call it, and provide data at higher cadence. So this is really exciting development and a good use of remote sensing observations.
Excellent. Thank you.
Okay, now we'll hear from our next speaker, Hyunki Lee, whose presentation is titled A New Data-Driven Inundation Forecasting Technique, Forecasting Inundation Extents Using Rotated Empirical Orthogonal Function Analysis, Fear, and its Economic Impact on Lower Mekong.
Yep, that works as well.
Right. Hello, everyone. So my name is Hyunki Lee from University of Houston. So today I'm going to talk about our new data-driven inundation forecasting technique that we named FEAR and its potential economic impact on Lower Mekong. So I would like to acknowledge my team member, Ching Chang Sondo, Tien Du, so Faiza Hossein from University of Washington, Kel from SEO, Tanapon, and Chinapon from Survey Mekong. Right, so we all know that people in Lower Mekong is well adapted to seasonal flood cycle. As you can see from those floating villages around the Twin Sep Lake floodplains in Cambodia. However, the people are still highly vulnerable to the extreme events. But the existing methods, such as using hydrodynamic models or GIS-based techniques, such as HANDS, may be too complex or less skillful over these large and flat terrains in Lower Mekong. So our purpose was to build a simple but skillful approach for the inundation forecast. So we named this technique Forecasting Inundation Extents using RUF analysis, or FEAR in short. So the first framework has been built over the 27 lake floodplains for the daily hindcast and forecast of inundation extents. So the idea is pretty simple. We just wanted to utilize the correlations between the historical inundation extents that we can obtain from satellite images and the historical river levels or stream flow. So what we did is we used the set of SAR intensity from Sentinel-1 images, and then we applied this rotated empirical orthogonal function analysis, and then we obtained the several significant modes, which consist of spatial patterns and temporal patterns. And then we can generate regression models between the temporal patterns and the historical river levels of the region. So as you can see, we have 4 regression models built from 4 different modes acquired, extracted from the SAR intensity images. So once we have the regression models, then whenever we have the water levels available for the future or for the past, then we can use that water level with our regression model. And then we can predict the corresponding temporal patterns, which could be in the past or in the future. And then we can integrate that temporal patterns with the spatial patterns and synthesize or generate the SAR-like images. So that SAR-like images will represent the simulated SAR images, which could have been obtained in the past or will be obtained in the future. And then by applying the any like water classification techniques, then we can obtain the hindcasted or forecasted inundation extents. So this animation represents the daily forecasted inundation extents over the 27 Lake floodplain for the year of 2019. You can see the dramatic changes in the inundation between the dry and the wet season. So after all, we were able to develop this new data-driven approach, which is easy to implement with the negligible computational burden. Okay, so our next step was now to build an operational inundation forecasting system for Lower Mekong, which is easily transferable and highly scalable to other regions. So we named it as FIR Mekong. And thanks to the teamwork with Survey Mekong and SEO, we are able to overcome these technical hurdles, and then we were able to build an automatic cloud-based tool, which has been the back end of this web application that we built using Streamlit. So Streamlit is an open source Python platform which help us to create and host the web applications. So you see there is a URL here. Anyone interested in can also take a look at this. But basically, this operational app is going to give us the up to 18-day daily inundation forecast over the region, and also daily hindcasted inundation extents from the year of 2008. And at the back end, we need the forecasted water levels. And for that, we used our in-house altimetry and VIC-based river level forecasting system over the Mekong River Basin. Okay, so here it shows an example of 18-day lead time forecasted inundation extents for 2021, and also a hindcasted inundation extents for year of 2018 as examples. So you can see the changes in their hindcasted or forecasted inundation extents. And this part shows the overall accuracy and also the critical success index for different lead times, as you can see. And also here's the temporal correctness rates. So it's just the percentage of times whether we have classified correctly, whether that's true negative or true positive. And next step is now to also generate the forecasted inundation depth. Now to do that, now we need a DM, similar to what Franz used. So in this case, we just use the Merit DM. We just pick that DM in this region. And also we have used this flood water depth estimation tool, which has been developed by the University of Alabama group, which is open source. So we grab that along with the DM, and then we also forecast the inundation depth from our inundation extents. Now we paused a bit here and we thought about how we can really make this useful for the people in the region. So we looked at a case study of forecasting, actually delineating the extents of the rice paddies, which could be predicted to be under flood damage. So it has been, according to an MRC report, if the rice paddy is flooded longer than 5 days with water depth greater than 0.5 meter, then they consider that rice paddies to be damaged due to the flood. So because we have now daily forecasted inundation depth map, we can also create the depth, the extents of the rice paddies, which will be predicted to be under the flood damage. So as can be seen in this right-hand side, these dark purple areas represent those rice paddies predicted to be under flood damage. Now we step further, and then we wanted to also estimate a dollar value. So we were able to predict the flood-induced rice economic loss using these equations. Because if you look at these equations, there is this total number of pixels that are under flood risk, also the pixel-wise rice relative damaging percentage. And we can obtain that from this so-called relative damage curve for rice over Mekong, which has been published by MRC in 2009. So you can see that that damage is being increased with a greater flood depth and longer flood duration. So from this, we can obtain that damage curve along with our forecasted inundation depth. And then with all these informations of the rice market price and rice yield, at the end, we were able to estimate the rice economic loss over in Cambodia and Vietnam for the years of 2020 and 2021 as examples. So as you can see, in summary, over $86 million USD and 1.5 million USD in Vietnam has experienced this economic loss of the rice paddies due to flood in year of 2021 during the wet season harvest time. So it means that if fear has been available with the region, this much of money could have been saved. And also the similar analysis can be done also for different land cover layers as well. Not only the temporal analysis, but we also show the spatial area, the locations where we expect to have a severe rice damage based on our analysis. Okay, so now there is also another case study that we wanted to do using our fear technique, but along with the hydrologic model called HYPE and the reservoir operation scheme called IROS that we have already set up in the region. So this, so the hydrologic model has been published by Tien Du, and also the IROS has been also published in WRR this year by Tien Du as well. So using these two, HYPE and the IROS reservoir operation scheme, we can simulate the water levels at the stations called Krati, which is located in the Mekong main stem, with different scenarios. So we tested here two different scenarios. The first scenario is that what if we have no reservoirs in the Mekong, actually in Trias Basin in this case. The second scenario is that, okay, what if all the current and the future planned reservoirs in Trias Basin become operational? So this time series of the water levels shows the differences between these two scenarios. So we obtained that predicted water level at Krati, and we use that as an input to our fear system to also simulate the inundation extents in downstream. So you can see these differences between scenario 1 and scenario 2, and you can see there is a dramatic differences in the inundation. So our next goal is to actually expand this scenario analysis to the entire Mekong Basin, including those controversial dams in upstream China as well. So here's the conclusion. So we can simulate the inundation with also different reservoir operation scenarios with negligible computational burden, which can be also highly scalable to other flood-prone regions as well. So here, for example, we also built something, well, it's actually the ongoing work for the FEA Bangladesh, so which has been used to also simulate the inundations over Bangladesh. However, we have one limitation, which is we can only simulate the riverine flooding. So if there is a pluvial flooding, we have to also consider the precipitation as well. And also it is highly dependent on the accuracy of the forecasted river levels and the stream flow as well. So here we have two relevant poster presentations for tomorrow by Chung Cheng, also already happened this morning by Tien Du, and I will be happy to answer any questions.
Thank you so much. Any questions out there?
About the river bathymetry. So river bathymetry, like I saw that you kind of highlighted active area. So how do you get the river bathymetry for cross-section area?
We haven't used any river bathymetry data, no cross sections. We just use the DM to obtain the inundation depth from the inundation extents. Yes, Robert.
That was great, thanks. So can you just talk a little bit about why the predictability for the seed drop out after 10 days? I don't know if I caught that. You mentioned on one of so many days out.
You mean this one?
No.
Yeah, sure. So as the lead time increases, the accuracy or the CSI is going to decrease.
So what's special about 10 days? Why do you think it dropped off?
I think that is dependent on the accuracy of the river levels that we use to obtain the inundation extent. So we use the JSON altimeter, which has a 10-day repeat. So that might be the reason, because to fill the gap in between 10-day river level observations that we obtained from altimeter, we use the VIC model to fill the gap. So perhaps that's relevant to that.
Great. We'll move on to our next one. So we have a canceled presentation, so we'll just move on to the one after that. So the next presentation is from Alessandra Nguyen Zwan, who will be presenting on estimating ecosystem services in a mangrove biosphere reserve.
So, hi everybody. I'm going to present the result of a project which is still ongoing, and is a project called Oversea, which is funded by the Italian Space Agency. And the partner of the project, beside the Italian partner, are the NASA and the Vietnamese Space Agency. So the focus of this part of the project is the assessment of the ecosystem services related to carbon sequestration potential in a special area, which is the Kanjo Mangrove Biosphere Reserve. Why mangrove? Because mangrove forests are a very high value ecosystem in all the South Asia area, and they exert a lot of function. Beside, they deliver also several services. In the last decade, but this kind of ecosystem were highly threatened by a lot of pressure, both anthropogenic ones and from climate change. This kind of ecosystem can benefit, this kind of ecosystem services assessment can benefit from satellite data that can help better understanding land use changes and their effect on the ecosystem services delivered by mangrove forest. So the objective of the project is to develop a geospatial model based on Earth observation data, both hyperspectral and multispectral, and using this kind of data together with the field measurement. The final aim, which is still to come, of course, is to build up an operational services to assess the carbon sequestration potential of this kind of ecosystem. Few words on the study area. Kanjo Reserve is a huge reserve, which is considered as the lung of the Ho Chi Minh City, and is localized in the southern coast of Vietnam, quite near to the Ho Chi Minh City. It is a highly threatened area and is a very evocative area because during the Vietnamese War was highly impacted by Agent Orange. So this kind of area is threatened by several pressures. Anthropic ones are mainly due to aquaculture plants and urban settlement development, mostly vocated to tourism. Land use changes are producing an impact because they are producing a shift from the carbon sequestration potential and coastal protection potential to another kind of services, which are the food provision ones and the recreational ones. So it would be very interesting to understand which are the trade-off between these kind of ecosystem services. To assess the carbon sequestration, we adopt a model, which is a combination of 3 existing models that are listed in the slide. And the main parameters to run the model are the FPAR and the light use efficiency. These two kind of parameters are ingested by the model to produce a GPP, a gross primary production assessment. And then from the GPP, it is produced the carbon sequestration assessment. Which kind of data we used? We used both satellite data and field data. The field data were collected on a campaign on the last October and were mostly spectral signature and PAR values and leaf area index values. Satellite data that were available are Sentinel-2 data and Prisma data, which is the Italian hyperspectral sensor. Beside this kind to optical data, we also use the SAR data coming from the Italian center, which is Cosmos Climate. Here you can see the workflow of the activities, the leaf-array index map and the FPAR map were used to feeding the carbon sequestration model, together with some climate settings from the Copernicus climate services to produce the GPP maps and the carbon sequestration maps. So these are the main geospatial products that were obtained. And beside these kind of products, we go deeper into assessing the land use change, especially with regard to aquaculture classification. In the slide, you can see the leaf-array index and the FAPAR map. And for the 3 years we consider, so from 2020 to 2022, FAPAR and LI are very important because they are essential climate variables needed to model the leaf density, the phenology, and the photosynthetic activity of the mangrove forest. One of the main issues with the satellite data was due to the cloud coverage, which is almost always present in this area. So there was the usable satellite data were very scarce. And but we can use at least 2 Sentinel data, 1 Prisma data, so 2 multispectral data and 1 hyperspectral data. As you can see by the lower maps, which represent the FPAR values, they are lower in the boundaries of the reserve. So we hypothesize this is due to the land use changes that it's occurring on the border of the reserve. We have the possibility also to validate these maps with the in situ field measurement, and the correlation spans from 40% for LI from Sentinel-2 and to 83% for LI from Prisma data. And for FAPAR, we obtain 58% of correlation. So going to the result of the running of the model, we got the gross primary production maps and the carbon sequestration maps. As you can see by the bar chart on the right, the cumulative curve, the cumulative values for the 3 data are very clear. There is a decrease for both gross primary production and for carbon sequestration potential. There is a clear decrease that we try to explain. The first observation we have is that maybe the border effect, which is visible at especially in the FPAR maps, could be due to the spreading of the aquaculture plants, because a lot of aquaculture plants were installed on the border of the area, not inside the mangrove forest, the reserve, but very close to the border of the reserve. And the other explanation we have for the extensive change in the FPAR could be related to a change in the environmental conditions, such as salinity, that changed from 2020, in which it was 20 PSU, and while in the 2022 it reached 34 PSU. This change in salinity, coupled with a change in air temperature, could lead in a decrease, or could affect at least the photosynthetic efficiency of the mangroves. So we decided to go deeper in the understanding of the land use change and observing the changes in the land use of the mangrove forest area. We see that between 2000 and 2020, we have a lot of land use changes on the border, exactly where we observed lower FPAR values. So we use also SAR data to understand where these aquaculture plants are localized. And we produce a flood map minus the existing persistent river channel. And in the end, there was a lot of land use changes also within the mangrove area. This is a focus on the northeast area of the reserve. And as you can see from the map on the left, the FPAR values that are lower are localized mostly where there is a lot of aquaculture plants. So in the end, we assume that FPAR could be considered as a proxy for land use change. And of course, this kind of approach should be refined, and we have to work a lot on this in the future, but would be a perspective or a promising approach. One issue we think it would be very interesting is to understand how this change in ecosystem services from namely from the carbon sequestration potential into a food provision potential could be accepted or could be acceptable. So which is the trade-off between these two kind of services? And understanding this kind of ecosystem services potential could help institutions to take action and have information useful to adopt new policies or planning action.
Thank you. Are there any questions?
Hi, I really enjoy your talk personally. My question for you is, can you elaborate on the connection between temperature change and salinity change to the observed decline of mangrove and sequestration?
At the moment, there are only hypotheses because we have to, the processing was done only in the last few months. So we are trying to explaining this kind of effect, but for now they are just hypotheses.
Just hypotheses. Okay. Thank you so much.
Yeah, go for it, Franz.
Wasn't sure if there's time for a second question. You said somewhere in a later slide that you were doing agriculture mapping from SAR.
No, not what it was aquaculture mapping.
Yes, agriculture
Yes.
extent mapping. Can you elaborate what approach you were using for that?
I'm sorry, I could not answer your question because I just jumped in the project. So
Okay, no
I'm
worries.
sorry.
It was aquaculture mapping, right?
Yes,
Yeah, so
aquaculture.
aquaculture.
Okay.
So
Yeah, I was more
He was
interested.
asking
It's
me
like,
what kind of process.
okay, flood detection. Okay. Perfect. Thank you.
Thank you very much. Our next speaker will be Nguyen Brawl, presenting on the effectiveness of land trender optimized temporally stabilized composites for enhancing the lower Mekong regional land cover monitoring system.
Yes. This one. Hello, everyone. My name is Nye, and I'm from Asian Disaster Preparedness Center based in Bangkok. Today, I would like to present effectiveness of land trender optimized temporary stabilized composite for enhancing lower Mekong regional land cover monitoring system. So these are the content of today's presentation. So first,
this ICMS is part of Savia Mekong project funded by USAID and partnership with NASA and Oregon State University and other private stakeholder. So in the previous few years, we developed regional land cover monitoring system to help Lower Mekong need assessment to address climate change adaptation, land use, land cover planning, agriculture planning, and disaster risk reduction. So you can also look our version 1 of land cover in this land cover portal, and this figure is the example of our land cover, regional land cover with the 18 different biophysical layers. So the left figure is the modular system architecture of our existing system. So we have reference data and satellite image. So we use those data and we perform mapping. We use machine learning mapping algorithm and leveraging in Google Earth Engine to map different primitive. And after that, we use Monte Carlo assembly algorithm to create a land cover typology, and then user can tailor their own land cover based on their need using that algorithm. And there are some challenge in our existing architecture. So we would like to address these challenges. So in today's presentation, I would like to highlight only one. So we have some problem like year-over-year variability in our satellite image. So we want to create temporarily stabilized composite for our regional land cover. So what we use is land trender optimized image created from Oregon State University. So we use that image in our land cover. So this is the overall system, how to create land trender optimized image. So land trender is temporal spectral segmentation algorithm to address land cover change using Landsat image. So here they ran clustering algorithm and use land trender index and parameter to create optimized image. So these are the example outputs of originate composite, regional composite, and land trender stabilized composite. So what we want to do is we would like to know how effectiveness this land trender stabilized composite for regional land cover. So we did 2 use case for Cambodia and Vietnam. So for case study 1, we analyzed 20-year comparison of evergreen forest primitive in Cambodia and Vietnam. So in this figure, this one is the training point of evergreen and other distributed over the 2 countries. The red is the evergreen. And to train our random forest model, we have different 56 covariates. But we don't want to use all of this covariate. We only want to use most important feature from that covariate. So we perform some feature importance analysis in there in Earth Engine, and we select 20 most important variables from them and train our random forest model. And these are the example output from our model. So if you look into this figure, these are the probability distribution of evergreen random forest classifier. And then you can see transparent distribution between evergreen and other classes for both regional composite and stabilized composites. And if you also look into the graph, the green color is the overall accuracy of stabilized one, and the red color is the overall accuracy of original composite. And there are only very small difference in accuracy. And most of the year, the stabilized composite outperform 0.5 to 1.5% higher than the original composite. And also same for the kappa. And this is the example result of 2002 and 2020 land cover. And the color show the probability. So the yellow and white color is 0, and the violet color and red color are 95 to 100. And you can see most of the evergreen area can detect well with the accuracy of around 19 to 95 or 96%. for both year. And for case study 2, we did 20-year comparison of deciduous forest. So the structure is the same. So we have training data. We did feature importance selection. And this is the probability distribution of deciduous. But the thing in here is deciduous forest, its phenology is changing every season. So, and also there are some noise in our data. So in here, it doesn't perform well like evergreen, but we can see clear distribution between 2 classes of deciduous and other. And also, if you look into the graph of accuracy assessment, you can see most of the year, the overall accuracy, the green check of the stabilized one is always outperform like 1 to 2% accuracy than the original regional composite. And these are the output results of 2002 and 2020. But if you look for this output, you can see some yellow and orange color with the lower accuracy around 15 to 60. But some area it can detect well with accuracy around 85 to 90, 92, something like that. And next one is, I would like to discuss what we found out from this two case study. So in here, like there are some cloud cover. The above 2 figure is the regional composite and output from the model, and below are the stabilized composite and output from stabilized. So if you look into this image, like there are some cloud cover in this area and also in here. And if we train the model with that one, in our output, like some area has some gap and the accuracy also drop, and there are some noise in our image. But with the stabilized image, we can detect where in that cloud cover area, and also in the same for this one. And next one is the SLC of. So after 2003, there is the SLC of in Lancet. So some area experience that problem, and mainly in northern Vietnam, most of area was affected by that. So you can see many strike noise in the original composite image and also many gaps. And you can see also in the output, there are many noise in the output. But with the stabilized composite, we can fix and also we can enhance the accuracy, we can enhance the output of classification. And next one is for the mosaic key problem for deciduous. So as I have told, deciduous phenology is changing every season. So when we create our regional composite, we use median of cloud-free period. So maybe in summer, so their phenology is a little bit low. And in that case, what happened is we experience omission error. So we cannot detect deciduous forest with the original regional composite. So in here, we cannot detect where. But with the stabilized one, we can detect where in this area of deciduous forest because it's stabilized the spectral pattern. And the next one is the agriculture. So this is the agriculture. The previous year, it is forest, but they changed to shifty cultivation. So, but in here, both regional and also the stabilized one, they cannot fit well for that one, for this certain phenology change. So these are the key takeaway from this presentation. So the stabilized one improved the stability of imagery for annual mapping. And there are also places that have artifact and cloud issue are mostly corrected in optimized image. And the random forest classification of optimized composite normally outperform than regional one. And there are some limitations to capture certain change from forest to cultivation in some area and also seasonal phenology change pattern area. Thank you.
Are there any questions? I'm curious, were there any sites that you saw like after running Land Trender that had originally identified incorrect changes, like specific, either like urban growth or
Yes,
No, like,
there,
specific-
we also see some urban growth change, but normally this land trend, they normally fit for the forest and that crop type. So for this presentation, I just only prepared two. We also ran for the rice and urban, and also it also improved also in accuracy and also in the actual visual inspection.
Okay.
Yes,
Thank you.
thank you.
I just asked.
So we do have one online presentation to end. Is Hanik Lak here to present? Or online, I mean, or in person?
Did not receive a video, I believe, so we'll double check. Okay, and Hanik Lak. With the, okay, so that may be our last presentation.
Yep, I think that's our last one then. Thank you so much for attending this session, everyone. We heard so many great presentations about many very diverse but interconnected environmental issues in the region, and about how Earth observations can help us understand and act on them. So we really appreciate your attendance here late into the evening. Yeah, they were all really great presentations. We learned a lot. Thank you so much.
You're curious about Servier? We're here and we can tell you more. I was like, oh, I think I did this. Yeah, and then it was a lot of people here. This one. Doors.
You feel amped now.
My face was so hot. And I was like, I asked a really stupid question. It was just very obvious. It was just like, yeah, not better, less food, more volume. I don't know. I didn't know. Yeah. Well, so the reason I thought that her. Yeah.
Yes, I'll be here till Monday.